Hey everybody, I'm going to walk through an example of using a Taylor polynomial to estimate a value. And I'm going to start by opening up my Octave program, and you should be using the GUI version. This looks a bit different than MATLAB, but it has the same basic windows that show all the same basic things, and a lot of the commands are exactly the same. This is going to pop up here in your command window every single time you open this, because it's a free software, so they have to say that and talk about source code and talk about disclaimers and all that stuff. But you can clear this out the same way we did in MATLAB, just by typing in CLC. The one thing you'll notice here that we're missing is an editor window. In MATLAB, we had to go in and we had to select a new editor. But here in the command window, if you look all the way at the bottom, there's actually 4 tabs open in this little sub window here. Remember, the command window is the one that we use as kind of a calculator or a tester. If we just want to type in a line or two of code and see what happens, we'll do it in the command window. But when we're actually ready to write our programs, we do them in the editor. So this is where we want to be. And I've already written some sample code for this program, and I'm going to share that with you. But before I do that, I would like to point you to something in, let's see, I want to go to our textbook. And there is a copy of the textbook in Connect. And on page 103 in our textbook, which is at the beginning of chapter 4 in section 4.1, also in our lecture notes, this exact formula is not in the lecture notes, but the whole concept is. So what we want to employ here is a stopping criteria. How do we know that what we have calculated is close enough to what we're looking for? So there is this formula that Scarborough came up with all the way back in 1966 or even before, that says if you want your calculation to be accurate to n significant digits, then this is the value you should use as your stopping criteria, and this is a percentage. So we would want to compare our percent error that we're getting in our problem with this one, and continue including additional terms in the Taylor polynomial until our percent error comes out in this value. So this value here is going to be hard-coded into our program. N is going to be coded separately, but this value is this is a fixed formula that we use quite a bit to tell us whether we are in the range of accuracy that we're interested in. So this value is going to be in there. If you look at the assignment, the programming assignment, I've already gone through and I have developed a 4th degree Taylor polynomial for e to the 2x that's centered at x equals 0. And as I said in some of the notes here, the more terms that we include, or the closer that we are to 0, the better the approximation is going to be. So we aren't necessarily going to know at the start of the problem how many terms we want to include. So our goal instead is to recognize the pattern in these coefficients, f of 0, f prime of 0, f double prime of 0. And if we can recognize that pattern, we could use the pattern in the code to extend out this polynomial to an infinite number of terms. So you'll notice that the relationship between these terms is that they're all powers of 2, starting with 2 to the 0. So later on, I actually give you, oh, where did I do it? Oh, no, that's not it either. There we go. I actually wrote out using an nth term, what exactly the terms of that Taylor polynomial are going to look like every single time. So if you only want it to be a 0 degree Taylor polynomial, you would only do this for I equals 0. I'm on a mistake, sorry. The n's here in the formula should be i's. Sorry about that. If you want a first degree Taylor polynomial, you let I equal 1, and so on. So fourth degree Taylor polynomial, you let I equal 4. In our program, we don't necessarily know exactly how many terms we want. What we're going to do is we're going to generate a whole bunch of them and find where we have a partial sum where the difference is within that acceptable range that we saw in the textbook, which we call our stopping criterion. So I'm going to pull up the program I wrote finally. You are welcome to use this same program, but this is not the program that will solve your problem. This one uses some slightly different numbers, so you're going to have to go in and change the numbers to get it to do what you want for your program. So I've already got this done, so I'm just going to go ahead and open it, but you would just make sure that you are in your editor window when you start typing your program. If you're in your command window, you won't be able to save it as a program. So make sure you're in your editor window. And I'm going to go ahead and open one that I've already got created. And this is my Taylor polynomial approximation program. So I'm going to walk you through step by step what exactly is going on here and what I'm doing and why I'm doing it. As with all of our program assignments, make sure that you're starting it with your name, the class, the semester, and the title that you're giving the programming assignment. This one is a Taylor series approximation. I've also included a description here because I want you guys to be able to access this program and understand what my variables are representing. So this program uses a Taylor polynomial specifically for e to the 2x, centered at 0. I am going to calculate an estimate for e to the first power to 8 significant figures, which means to the nearest millionth. And what that means is because my program is for e to the 2x, if I want to find e to the first, that means 2x is equal to 1, which means x is equal to a half. So I'm going to be running this program with x equal to a half, and n is equal to 8, because that's the number of significant figures that I want my answer accurate to. So I've defined these values. I have programmed x equals 0.5 into Octave, and I told it that this is, I want to use this value because this is the value that will return e to the first when using this Taylor approximation for e to the 2x. I've also told it I want n to equal 8. That's the number of significant digits of accuracy that we want. And then I've also programmed in this stopping criterion, which I called error, and I just abbreviated as ERR. So this is the exact same formula that is in the textbook. The only thing I did not include is the percent symbol. So we'll have to remember later on this value is a percent. I've written my program to run based on whether or not the current difference between any two terms is greater than this acceptable error. So in order to calculate error, I've got to have two values. So another thing that I decided to do here is I hard-coded in the first term of my Taylor sum, which in this case is equal to 1. If you look back at the assignment, when we set up our Taylor polynomial here, the very first term is a constant and it's equal to 1. So I've got to let it know that, because it's got to start with two values in order to find the difference between them and calculate an error. So I've already started it with the first term of our Taylor sum. And I'm letting it know that that first term is the 0 term. It's what I get when I plug all zeros in to the formula. So our formula up here would only include this piece. To do a 0-degree polynomial, I need to calculate the 0 derivative of f at my center, so f of 0, which is equal to 1, and then x minus c to the 0, which is also equal to 1, all divided by 0 factorial, which is equal to 1. So we've got 1 times 1 divided by 1, which is all equal to 1. And that's why our first term here is just a 1. And that's considered the 0 term because 0 as an index was used to create that term. And I'm going to start with a percent error of 100, which obviously is the maximum amount of error. Well, theoretically. Certainly we would not expect more than a percent error of 100. So I start this value out pretty large, knowing that I need my program to run at least once. And you can always check to make sure that this is true, that the percent error that you chose to start with is less than your ERR, is greater than your stopping criteria, so that you know this will run once. So if our percent error is greater than our acceptable error, then I need to add additional terms to my Taylor sum. So the first thing I'm going to do is I'm going to add to my counter. This counter tells us what degree polynomial was required to come up with the approximation, and it also tells us how many times we had to perform this loop to get to that value. It also represents the number that's being plugged in to our formula here. So that count serves multiple purposes. It's a count of the degree, a count of the number of iterations. It's also representing the 1 here in our Taylor polynomial formula. Notice the next term has 2's in both of those spots, and the next term has 3's in both of those spots. The only thing that's ever going to be different when we change functions or we change centers are these values, those coefficients, 1, 2, 4, 8, 6. And that's where I got the 2 to the n portion of my formula. The n factorial is already part of the Taylor formula, and x to the n, if we're centered at 0, is already part of the Taylor formula. The only thing that's unique to this particular function is that 2 to the nth power. So I added 1 to my counter. This is going to change my counter value to 1, and it's going to include a linear term in my approximation. And I get it by plugging 1 into that Taylor formula. So I want to create an additional, another sum. And I don't yet want to replace my previous sum because I'm going to need 2 sums to subtract and divide in order to come up with a percent error. So I want my next sum to be my previous sum plus whatever the next term would be in the Taylor series. So for this one in particular, we've got 2 to the n power, which is count, times x to the n power, which is count, divided by the factorial of n. That will give me the next term in the Taylor series, and it will add it. So I now have a partial sum that's 1 degree higher. I would need to find the percent error between these two values because we don't want to quit until that error is acceptably small. So to calculate percent error, we really don't care which one's larger and which one's smaller, so I'm using an absolute value. We need to calculate the difference between the previous sum and the next sum, and divide it by the previous sum. That will give us a percent change, and then times 100 will turn it into a percentage. Remember, this ERR up here was a percentage, so we want to make sure that we're comparing percents with percents. And then we want to turn our previous sum, which was just 1, it included only one term. We now want this next sum value to replace it. So I have assigned the previous sum to now take on the value of the next sum. Since we're done with the while loop, the way that a while loop works is it's going to go back and it's going to check this again. Now, we didn't change the ERR value, but we did change the percent error value based on this new term. So it's going to check and see if the addition of that new term was enough to get us as close as we want to be. If it is, then it's not going to calculate all this again. It's just going to spit out our answer and what degree Taylor polynomial we needed in order to get it. But if our percent error is still fairly large, really anything larger than the acceptable error that we programmed in here, it's going to do this over and over and over again. It's going to go on to the second degree term, and it's going to take the first partial sum and add in the second degree term and calculate a new percent error and replace the previous sum with our new sum, and then check again. And it will keep doing it over and over and over again until we get 2 successive terms that are within this amount of each other. Then we know for certain that our answer is accurate to 8 significant figures. We could always come in and say, well, I don't need it to be that accurate. I just want it 6 significant figures. We also could say, well, I don't want to calculate E of 1. I want to calculate E of, let's say, 0.2. And in that case, remember, that exponent is not the same as the x because our function is e to the 2x. If I wanted to calculate e to the 0.2, I would have to set 0.2 equal to my exponent here, and I would see that my x value really should be 0.1. And then I would need to change it here. And then I could run the whole thing. Everything's exactly the same. I'm going to go in and change these back to what we started with. We're trying to estimate e to the first power using the e to the 2x function. That means our x value is 1/2. So let me fix those. And we do want this accurate to the nearest millionth, which is 8 decimal points. And I'm going to go ahead and run it, and we will see what happens. So in MATLAB, we're used to seeing the output display here on the same screen. In order for us to see the output, we're going to have to go down here and click on the command window. So it looks like it took 10 iterations. So we had to go out to a 10th degree polynomial. And when we did that, we got 2.718281801146385. If you didn't get a number with that many decimal places, what you need to do is add one more line at the top of your program and tell it to format long. Most likely, you might just be showing 4 decimals here, and it would be impossible for us to convince somebody that we're accurate to 8 decimal places if we only show them 4. So format long will actually show 15 decimal places. And because we're in the command window now, if you want to, you can ask what the exact value of e to the first power is, and then we can see that these match 2818 all the way down to the 2 here, which is 1, 2, 3, 4, 5, 6, 7, the 8th decimal position. And that number's familiar. Where did we hear 8 before? That is the number of significant figures we wanted it accurate to. So there you go. Please put format long in your program so that we can actually see. You could use the same program, but you're going to have to go in and change the x values because you're being asked to calculate a different approximation. Also, make sure that you are displaying all of the output here at the bottom that the instructions are asking you to display.